Okay, good morning, everyone. Welcome to the GIST Sea Level Rise seminar. We're very glad to have Dr. Yixi Zheng, who is a postdoctoral researcher at the University of East Anglia, United Kingdom. And her research interests include questions in physical oceanography, particularly those regarding interactions between oceans and ice shelves in Antarctica. Dr. Zheng received her PhD in physical oceanography from the University of East Anglia and a bachelor's in physical oceanography from the Ocean University of China, Qingdao, China. In 2022, she received the International Association of Cryospheric Sciences Early Career Scientist Prize for her paper on reversal of ocean gyres in the Amundsen Sea. And today she will be speaking on the topic, the interactions between ocean ice shelves and sea ice in the southern Amundsen Sea. Welcome.
Yeah, thank you so much. And thank you so much for inviting me, and thank you so much for organizing the whole thing. And I'm super glad to have such an opportunity to just share my science. Can I try to share my screen now? Is it working? Can you see my screen properly?
Yes.
Yeah. Give me a second. Okay. Just trying to remove the Zoom thing. What about now? Everything's good?
Yes. Yeah, that's good.
Nice. So today in this seminar, I'm going to talk about the interactions between ocean ice shelves and sea ice in the Southeastern Amundsen Sea in the Antarctica. This part of work is actually based on my oh, I couldn't find my cursor at all. It's really strange. Sorry for the technical part. Is it something common?
I think I can see your mouse.
Yeah, I guess I might have to do this. What about this one? So then you can see my cursor. Okay.
Yeah.
Nice. Yeah. Oh, gosh, such a bad start. Sorry. But then, yeah, I will just continue. So this part of work is based on my PhD work. So I want to spend a bit of time just to say thank you to my supervisors, Karen, Ben, and Dave, and also of my co-authors, Betsy, Louise, Lars, Rob, Bryce, Sharon, and also 6 anonymous contributors. Those are our SEALs from the Southeastern Amundsen Sea. They actually have names, but it's just I can't remember their names now, so they have to go anonymous. But also with special thanks to Helen and Fabian and Mike, and also everyone who worked in those cruises that make these observations possible. And also the most lovely founding sources in the world, of course. And then here I can, gosh, is it still working? Right. So what are the ice shelves, and why do we care about them? So this one is the ice shelf of, is a schematic of the ice shelf. So we have the ice shelf here, and we have the ocean here. So you can see that the ice shelf in this part is actually floating above the water. And we care about the ice shelves because they are losing mass rapidly. So this map is showing the rate thickness change in the Antarctica. So with those parts, it is where the Amundsen Sea is. You can see those big and red dots. So you show that the ice shelves in the Amundsen Sea are losing mass rapidly. And we think that is because of the ice shelf ocean interactions. So that is because that in the Amundsen Sea we have the relatively warm modified circumpolar deep water, and they come from this region and then they go all the way into the ocean beneath the ice shelf, and then they can melt the ice shelf from beneath, and then cause very high meltwater rate, meltwater injection into the ocean, and also with the melting of the glacier, it's going to change the global sea level as well. And that is why that we studied this place. And so then there will be the first part of my talk, and it's also the first part of my PhD. Winter seal-based observations reveal glacial meltwater surfacing the Southeastern Amundsen Sea. So in this study, we try to answer two questions. The first question is, where does the meltwater go? And then the second is that glacial meltwater's fate in winter. Because we already know quite a lot about summertime meltwater distribution, but we never really know what's happening in winter because we don't have enough observations. Until those cute, happy faces come up to our mind, and then with those seals, when we put those small tags on the top of their heads, and then they can swim around in Antarctica, and especially in wintertime as well, and then collect the CTD measurements for us in this season that nobody can really go. And this part of work has been published already, and if you're interested, you can just try to look at our paper. And so then this one is the this one is actually a GIF. Apologize again that it's not showing. But this one is showing a very rapid retreat of Polynyas Ice Shelf. And so Polynyas Ice Shelf is one of the most rapidly melting ice shelf in the world. That is why that we chose this region as our target. And then this one is again the map of Polynyas Ice Shelf, and the difference is that for those dots, they are the locations of the siltec profiles collected from wintertime in 2014. And there are more than 600 profiles within just one season. So for many people here, you might know that for a cruise, for an Antarctic cruise, normally we can collect about 200 or sometimes 300 profiles for the maximum. But for the seals, they can collect a lot of data, and in this incredible season. And for those dots, I colored them by the near surface temperature above freezing. So for the blue part, it means that that's very close to the freezing point. And then for the red part, it means that it is warmer. So for those dark blue dots, it means that those areas have the near surface temperature close to the freezing point. And that is something that we are expecting because it is wintertime Antarctica. But then for those parts where we have those light blue patches, and then in here, even those kind of pinky and even red dots, it means that the near surface water here has the temperature above freezing to about 0.5 degrees C above freezing point. And it's quite extreme in wintertime because that's something that we are not expecting at all. Why is it so warm here? And so then to answer this question, we define two transects here, which are this pink one and then this green one. So one is perpendicular to the Polynyas Ice Shelf, and then another one is perpendicular to the ice shelf, and the one's along Polynyas Ice Shelf. So then we go to the first one here, and for this pink one, we have the x-axis from 0, that is the southwest, so that's from here, and then to the northeast, so that is here. And I plotted the wintertime transect and then the summertime transect shaded by the conservative temperature above freezing again. So then you can see that in summertime, the water is generally warmer than in winter for the upper ocean. And again, that is something that we're expecting. But then something that we are not expecting is that there are some light blue patches here, but there are those relatively warm columns. and in these dark blue patches. So those dark blue patches are something that, again, we're expecting because it is at the freezing point, and that's because it's in wintertime. But those light blue patches is really intriguing. So then we start thinking that what's making those things happening, for those pinky dots that we see near the surface, we think that's the heat that's actually transporting from beneath the upper ocean, from this very warm layer through those relatively warm columns. Then we start having an hypothesis that maybe there's actually heat sources from meltwater-rich water. So the reason that we are having this hypothesis is because of this. This is the schematic of the cross-section of a melting ice shelf. So then we have the floating portion of the ice shelf here, and then we have the ocean here. So for the ocean part, we have the modified circumpolar water coming towards the ice shelf, and then when the meltwater is coming out from the ice shelf, it's going to preserve the heat from the modified circumpolar water, and then transport it to the ocean outside of the ice cavity. And then to confirm this hypothesis, we then calculated the meltwater content. To calculate the meltwater content, we made several assumptions. The first assumption is that the fraction of the meltwater, and then the winter water, and then the modified circumpolar water are everything that is that's making the water column here. So the sum of the fraction is 1. And then another assumption is that the mixing among those 3 water masses is the only processes that is changing the temperature and salinity of our measurements. So then with those 2 assumptions, we calculated the meltwater content from our temperature and salinity from both wintertime from our sails and then from summertime from our ships for the same transact in 2014. Then we have those lower 2 panels. And then in summertime, we can see that for the upper ocean, we have a nearly homogeneous meltwater distribution almost everywhere. But then in wintertime, we have one layer of meltwater-rich layer that is at about 450 meters, and then another meltwater-rich layer above about 250 meters, and they are linked by those meltwater-rich columns. So it means that the near-surface meltwater-rich layer is actually formed by the water transporting from this layer through those meltwater-rich layers. And then we want to answer the question of why this is happening. So then we went to another transact, that is the transact that's perpendicular to the Python ice shelf. So now we have the x-axis from 0, that is at the Python ice shelf, and then to about 90 kilometers, that is away from the ice shelf. Then again, in the summertime, we can see that above about 400 meters, we have meltwater pretty much everywhere, and the distribution is relatively homogeneous. While in wintertime, and again, this layered structure is so significant that there's one meltwater-rich layer along this isopycnal here, and then another meltwater-rich layer near surface connected by the meltwater-rich columns here. So again, why is it happening? Then we think that it's actually because of the seasonal stratification in front of Python ice shelf. So in summertime, there are many gray lines here, and those are the isopycnals. Apologies for non-oceanographers. Those isopycnals are the density contours. So we have that in summertime with the combination of solar warming and also the sea ice melt. The upper ocean is very stratified. That is why we have those isopycnals here, and we can observe them in our in our ship time transect as well, with those lines aligning here. But then in wintertime, the thing has completely changed. The wind stirring and also the very intense surface cooling creates a very weakly stratified water. So now you only have this interface between winter water and modified circumpolar deep water. And above this, everything is relatively homogeneous. It's so weakly stratified that when the meltwater is rising up, it doesn't need to go through those density contours. And it can just rise up efficiently without mixing with the ambient water. And that is what we are observing here, that in wintertime, above this isopic node, everything is almost uniform, so then the meltwater can just rise up to the near surface. So why is it important? Here is a small summary of what we found. We found a seasonal variation of glacial meltwater's settling depth, and we attribute it to the seasonal stratification of the ocean in front of ice shelf. And that is super important because meltwater from the winter can transport heat to near surface and then melt the sea ice effectively. And then to form the polynya, to form a sensible polynya in this region, and then boost the air-sea interaction. And then another thing is that when the meltwater is rising up, it can actually transport the nutrient from the very deep water to the euphotic zone, and then boost the phytoplankton bloom in the next spring and summer. And that might potentially partially explain why there's so much high there's such a high phytoplankton primary production in front of Pine Ice Shelf and also all other ice shelves in spring and summer. And then another thing that we need to consider is that for the climate models, we keep thinking about what depth should we inject the glacial meltwater. And now our research show that we will probably need to consider the seasonal variation as well when we are thinking where should we put the meltwater into our climate models and coupled models in this region. So then again, if you want to know more about this, you can try to find everything from this paper here. So there would be everything for the first part. And then the second part is the reversal of ocean gyres near ice shelves in the Amundsen Sea, caused by the interaction of sea ice and wind. And again, this part of work has been published in the cryosphere, and you are very encouraged to dig more into this. Then we have this one. Why are we doing research about gyres here? So it's just because I've been seeing this gyre in front of Pine Ice Shelf everywhere. This gyre is called Pine this gyre is called Pine Bay Gyre, and it's been here in all models and observations. And the mooring data in this region has shown that it might have reversed its direction once in history. But then why this gyre is here? And also why did it reverse its direction? It doesn't really make any sense because there are those orange arrows, and those are the climatological wind field from the era 5. So I can't really show you, you have to believe me. Those orange arrows, they actually show cyclonic wind everywhere. So it means that the wind field in this place is rotating clockwise, cyclonically. So that is forcing this gyre here. So for this gyre, we sort of understand why it is here, because the wind forcing here is cyclonic. But then in 2019, in a cruise that I was lucky enough to get involved with, we found another gyre that is rotating anti-cyclonically, so anti-clockwise, And this gyre is rotating in a different direction as this gyre, and not just different to this gyre, but also different to the wind forcing in this place. So then it was like, it doesn't make any sense at all to me. And then if we step a little bit back about why do we care about these gyres, and that is because that many papers from recent years actually demonstrate that the gyres, you can see that they are all near the ice shelves, and they can greatly influence the melt rate of ice shelves. And then they can also transport the meltwater to everywhere, and then extend the influence of meltwater to a larger area that is further away from the ice shelf. So then they might contribute to creating a even bigger polynya, or contributing to boosting the phytoplankton bloom in area that is further away from the ice shelf. And then back to the question again, why here, and why did it rotate in different direction? Then we start thinking that when we are looking at this map, something that we notice immediately is that for this gyre, it is pretty much in an open ocean region. And this region is pretty much always open ocean in summertime, while for this gyre, it is located in a partially ice-covered place. And this place has been historically ice-covered for most of the time. So then we start thinking that probably this different sea ice condition is causing the different rotation. Then to prove this, we start running the MIT GCM idealized barotropic setup. So we have the schematic here. We have a square domain like this, and then we have the ice shelf here, and then we have the wind blowing off the ice shelf, and that is very similar to what we are observing in the Amundsen Sea. And for the wind forcing that we use to force our model, we are using a simplified version of what we are observing in the Amundsen Sea. So that is cyclonic everywhere, with stronger wind in the western side and weaker wind in the eastern side. Then we start forcing our gyre. And so for this one, we set one experiment that has the offshore wind blowing here, and with the forcing that I just described. And then for the other gyre, with the offshore wind here, something different with the forcing is that now we are setting a sea ice layer. And when we set up this sea ice module in our model, we actually didn't consider any thermodynamics of the sea ice model, but we only consider the wind, how the sea ice is going to impact the air-sea momentum flux. So for our first experiment, we just assume that the sea ice is going to block all the air-sea interaction. So then it means that there's zero wind stress here. And then we see the steady state model result. So for this Python gyre, we have the wind stress like this, cyclonic everywhere, and then we have the result like this. So this one is showing the stream function of the modeled gyre. And from the cyclonic wind, we have cyclonic gyre, and this is something that we think that will happen. And but then for this gyre, something very strange is happening. While we have the cyclonic wind forcing everywhere here, but because we have the sea ice blocking all the wind stress transferring from the atmosphere to the ocean, now now along this diagonal separating the sea ice zone and sea ice free zone, we have the blue line, the blue patches here, which means that we actually have positive wind stress curl. So that is anti-cyclonic. That is because when we have the wind here and then no wind here, what would happen is that there's going to form this sort of rotation along the diagonal. And then this anti-cyclonic forcing along the diapic node is strong enough to force an anti-cyclonic gyre. And that's exactly what we observed for the gyre near Thwaites Ice Shelf. And then to make our gyre model applicable to other regions in the Polar Ocean, and also as we all know that the sea ice might not just block the air-sea momentum flux, sometimes it might enhance it as well. So then we run different model setup with sea ice effect to the ocean made by a different percentage of the wind stress transferred to the ocean through sea ice. So here we set it as 20% tow and then 40% tow, and then we run over our model experiment until 200% tow. That means double the air-sea momentum exchange, and then to see what's happening. So then we realized that the gyres actually become more cyclonic when the percentage of the wind transferred to the ocean is increasing. And there's something that we're expecting as well, because again, cyclonic wind can force cyclonic gyre. And then another experiment that we were doing was that we changed the rotation of the sea ice front. Or the marginal ice zone in some cases. So that is the line that I showed you that is separating the sea ice free zone and also the sea ice zone. And then we change this front orientation and then see what's happening in our model. And then, that is another one. And then we conclude everything into this figure. I apologize, it might be super difficult for any human being to understand, but we've written a very detailed summary in this paper. So if you want to check this, you're super welcome to, super encouraged to. So then there's a conclusion here that the both wind field and sea ice condition play an important roles in the gyre circulation in front of ice shelves. That is because to generate gyres, all we need to generate a wind-forced gyre, all we need is just a spatial difference in the wind-induced drag. So this could be done either through the wind field itself, like in the Amundsen Sea, we have cyclonic gyre, or the sea ice affecting the wind stress transferred to the ocean. And then another thing that we notice from this work is that sea ice condition can modify the wind stress transfer to the sea surface sufficiently to just change a gyre direction, not just about the gyre strength. And why do we care about those results? It's because with the changing sea ice condition in the changing climate, the local circulation in the Antarctic shelf might be changing too as a result of the changing sea ice condition. And as we know that in last year, we had a very significant sea ice decade, and it might just change the gyre circulations in the Antarctic shelf seas. And this can also affect the melt rate of ice shelves. And you can read more in this paper, which described perfectly a very nice work by Thiago Dotto and the co-authors, how the gyre change is affecting the Thwaites melt rate. And then also another more efforts need to be put into the sea ice change and also how they affect the ocean circulation in Antarctic shelf seas. And then there will be everything. Another part of my PhD, I was working on the upper ocean processes in the Amundsen Sea in Austral summer, in Austral autumn. And then this part of work is in review in JPO now. I'm not going to talk about this in detail now, but it's just nice to show you that for this part of work, we did some really thorough study of the very high resolution dataset collected by SEALS again. in the Amundsen Sea, and then this allows us to get this stratification in the sea ice formation season, so that is autumn for the first time in this place. And then another work that I've been doing is just about the glider data set and then ship transact collected in front of Thwaites Ice Shelf. And I'm studying the meltwater distribution again, and then trying to see whether the temporal variation of meltwater distribution can be resolved by our high resolution glider transacts in this place. And that would be everything that I need to talk about today. Ray, any questions?
Thanks very much, Yixi. Does anybody have any questions?
Probably I explained everything too clearly. I'm sure that's the reason.
Well, I was wondering about the whether there could be like a positive feedback with the circulation there could like increase the sea ice, which could help perpetuate that circulation.
Yeah, I think so. But certainly we can't really prove it now with the limited observation here, because I feel like to prove such a positive feedback, we will need a long-term observation system in this region. But I completely agree. I think there's when more meltwater is coming, and also when the gyres are transporting meltwater, and especially the meltwater is relatively warm compared to the ambient water in this region, and they might just potentially cause the sea ice loss, and then causing a positive feedback in this place. Yeah, I guess we need more funding.
Any other questions? Because I was also wondering about the meltwater from the glaciers, whether that could, like cold water could increase sea ice, somehow having an effect.
I don't really understand your question actually.
Oh.
Yeah, can you say that again?
I was wondering whether if the meltwater is colder than the surrounding water, meltwater coming from the glaciers, whether that could help sea ice to form, which could affect the system in a different way.
Yeah, I mean, good point. But then the meltwater because in the Amundsen Sea, all ice shelves they are warm shelf, warm cavity ice shelves. So when you have warm water melting the glaciers, they let me try to phrase my answer quickly. So I think from our observations, because in wintertime in the sea ice formation season, and the upper ocean is so cold, it's always near the freezing point. So the meltwater is actually always warmer than the ambient water. So it can't really affect with the it can't really increase sea ice formation rate in wintertime in this place. But I guess in cold shelf, in cold cavity ice shelves, there might be the case because ice shelf water is much colder. But then my question became when when it's really that cold, it might just be too dense to really surface, and so then it can't rise to the near surface to form more sea ice. But yeah, but the meltwater is definitely affecting the sea ice formation in a way that, because meltwater is so relatively fresh, so when it rises to the near surface, it's going to create a very buoyant near surface layer, and making the water more stratified. It's like it's almost like a fresher cap, and so then with a more stratified water, everything, all the air sea interaction is going to be trapped in this relatively shallow mixed layer, this cap. Hope that makes sense.
Right. Okay.
Yeah. Yeah, if you have any more questions, feel free to just contact me. Every email is going to make my day.
Okay, great. Okay, thanks again. Thanks everyone for coming.
Yeah. Thanks so much for coming, and thank you so much, Patrick, for organizing this.